Hello, everybody. Well, if we could get started for the President's Plenary. Thank you. And do I have my first speaker, Clive? Are you, there you are. You're way in the back there. Perfect. So thank you, everybody. This is weird for me to give this announcement when I'm not wearing a mask, but make sure you're wearing your masks throughout this whole meeting, unless you are, in your room or actively speaking, giving your talk. Thank you, guys. I'm looking out and I see lots of masks, especially I hope you saw that you have some cool space masks in your goodie bag. So everyone got 5 masks and some hand sanitizers. And hopefully, everyone's got their social distance band. Go Team Yellow. I don't know. We'll all be in tribes by the end of this. But, I think we fixed the monitors, so hopefully we won't have any more problems for our speakers for today. So again, my name is Jamie Foster. I'm the president of ASGSR this year, and it is my prerogative to get to pick the speakers for the President's Plenary. And as we look away from low Earth orbit, we just had a wonderful talk about low Earth orbit and all the exciting possibilities that we're going to be able to participate in. But we also have to look a little further away. ISS, we have to look beyond the International Space Station and how we can expand our science to the moon and beyond. And so I thought that it would be really good for the community to learn a little bit about the moon and what has been done. And we have 3 amazing researchers going to give talks about different perspectives, different missions, and what do we know about lunar science, and how can our community maybe get proactive in thinking about research on the moon. So our first speaker is Dr. Clive Neal. He's a professor of planetary geology at the University of Notre Dame. Dr. Neal has been very active in all things lunar. He helped develop the Lunar Exploration Roadmap when he served as chair of the NASA Lunar Exploration Analysis Group. And he formed the LEAG Commercial Advisory Board. And then in 2015, he received the NASA Survey Institute Waco Award for his work. And he's published over 120 peer-reviewed papers. I haven't even hit 100 yet, so that's amazing. He has a really interesting one that came out in Science about young basalts, young being only 2 billion years old. So I think we're going to learn a lot about the moon, and he's got a great presentation called An Overview of Biological and Physical Science Research Conducted on the Moon. So without further ado, Dr. Clive Neal. No problem. And
it's all right, that doesn't work. I'm using my own
laptop. Oh, okay, sounds good.
Right. Thank you, everyone. It's great to be in a 3-dimensional meeting. It's been a while, and it's fitting if I say welcome home, because I can remember when you guys were sent packing out of the Science Mission Directorate, and I think it is welcome home because we have very exciting times. Shirisha's talk, did you sense the excitement in her voice? Did you sense that? This is happening beyond low Earth orbit now. This represents an opportunity for this community to actually push humanity out into the solar system. This is still flashing, by the way, so you haven't fixed it. So if I suddenly have a seizure, it's because of that. So I want to give an overview and talk about the moon, mostly what happened in the past. But I want to lead that into, I'm giving another talk on Friday about the future. And you will get a sense of how little I know, because this is a new community to me, but I'm here to prove you can teach an old dog new tricks. So I'm looking forward to this week to learn from you guys about how you can propel humanity out to the moon and beyond. And one of the questions I had for Dr. Zabukan was, okay, how much overlap or how much influence can human exploration have on SMD decadal surveys, because our science is what will propel humanity beyond low Earth orbit. And that excitement that we sensed in the previous speaker is going to build and continue. And as this is my third time seeing the United States vector back to the moon since Apollo, this is very, very different from the other two. So why the moon? Why the moon? And Dr. Paul Spudis, who's no longer with us, unfortunately, wrote this book, The Value of the Moon. And it can be summarized in 3 very brief sentences. It's close, it's interesting, and it's useful. Kraft Ericke, an Apollo engineer, made the statement, if God intended us to be a spacefaring species, he'd have given us a moon. We have a moon. It's close, it's interesting, and it's useful. But what does that mean in terms of how we move forward? It's an enabling asset for many things. Going out to explore the solar system, that first small step, or that giant leap, over 50 years ago now, was something to be beholden. And hands up, who remembers that first step in this room? Yeah, not many of us. But that small step ended 50 years ago next year. So this is what makes this new thrust towards the moon and beyond very, very important. So it is close, it is interesting, and it's exciting for science and exploration. And you can see the cover page of the League Lunar Exploration Roadmap that is a living document and gets updated as regularly as we can get new data into it. So, and again, it's the most accessible destination for realizing commercial participation, for creating new jobs. And as I work at the University of Notre Dame, I'm sort of very familiar with this question to graduates. What are you going to do after Notre Dame? And we're not that far off from them answering me, well, I'm going to go work on the moon. I don't think that's science fiction anymore. I think we're getting close to science fact, but there's a bit of work that needs to be done in that. So the other thing that our moon can do is to facilitate sustainable space exploration. The important thing about that sentence is that word, sustainable. Everybody uses it, but what does it mean? What does it mean? When you think of sustainable, what does it mean? Enduring? Long-term? Can we do it within our budget? What does sustainable mean? And I don't have an answer to that question, but I do think that the National Space Council in 2020, they published a document that actually defined it very well, and it's a 3-pronged approach. It is money, it is policy, and it is also return on investment. And I think that that's something to remember as we do value our science. Dr. Zabukan said, just doing it for science sake is important. Doing it for the good of society back on Earth is critical. And that is something that I think that space exploration can actually give back to society here on Earth. So what's happened on the moon since Apollo, or during Apollo? Well, you're looking at the only Apollo-era experiment still in operation that is actually with the Soviet Union, with 2 laser retroreflector sites on Lunokhod 1, Lunokhod 2, given there in the Luna 17 and 21. That's gone black again. So I think that we still are getting data from the moon to actually understand the cosmos. Well, what does that mean in terms of understanding the cosmos? Because there's a lot of great astrophysics that can be done with laser ranging. We have pretty much a 50-year record of that now. However, note where that network is. It's in the near side going up into the northern hemisphere, central near side up to the northern hemisphere, maybe out to the eastern limb a little bit. Nothing in the south. That represents areas that need improvement. Because in order to make improvements in our understanding of these astrophysics ideas, for example, the equivalence principle. I'm a geologist. I found out what the equivalence principle is and did a bit of reading on it, which means I don't really know that much about it. But what I do know is that lunar laser ranging can help test the equivalence principle. And that becomes important for basically testing some of the fundamental concepts that we have in that area. And again, if we look at lunar laser ranging data, they suggest that they are accelerating as predicted by the equivalence principle. But that's only on the basis of the current data set. If we then look at the general theory of relativity, again, this is borne out with the gravitational constant. From the current data set, this is not changing in terms of looking at the Earth-Moon system. But again, we really need to get more precise data. Well, what does that mean? Well, let's look at the inverse square law. Millimeter or less precision on our measurements. We can get to centimeter or less measurements with the current network and the retroreflectors. Now, those Apollo-era retroreflectors are degrading. The returns, you need stronger and stronger lasers to get good returns. But what about the next generation of lunar laser retroreflectors? Theoretically, they can give us the precision that are needed to make fundamental advances in testing these basic concepts that have become law, if you like, in the astrophysics world. The other thing that laser ranging can do is to tell us about the interior of the moon. We're looking at the physical librations and tides, calculating the love numbers due to the elastic properties that are measured by 50 years worth of data to the moon. And understanding that the moon does have a core, a small core, not a big one like the Earth, and that at least the outer portion of it is fluid. Well, when these results came out from laser ranging, everybody thought, well, the moon just thermally can't sustain that. And yet it does. So when I come back, the moon is interesting. It's fundamentally interesting because it's not behaving as predicted. Which again, in my mind, means that we have to go back because we now have more questions than we had originally and a lot more detail. To understand that interior structure is very fundamental to understanding how terrestrial planetary bodies start to evolve and differentiate. On Earth, that's all obliterated because we have plate tectonics, where we've got a lot more heat. We're still an active planet. The moon was thought to be dead. Then we started finding young basalts. Initially from crater count ages, now with the Chang'e 5 Chinese sample return, the first age dates from those basalts. 1.9 billion years old. That's young. That's young. Maybe other remote sensing data suggesting some volcanic activity as young as 100 million. Still needs to be tested. So there are important data that can be collected in terms of laser ranging that can help us understand how planets evolve, the fundamental initial differentiation of terrestrial planets. Once a magma ocean had been hypothesized for the moon back in 1970. In the 1980s, it was then hypothesized for Earth and Mars. Is the magma ocean the initial stage of terrestrial planet evolution? We don't know, but we can test it on the moon because All the basalts, even the young ones that have been brought back, conform with being derived from a source region that underwent processing through a magma ocean, or is at least consistent with that. So the idea is to put a New Frontiers 5 proposal in to put a lunar geophysical network back on the moon. It has one goal: to understand the initial stages of terrestrial planet evolution. And there's a number of different objectives that we want to actually pursue with a suite of instruments. Not going to go through each one here, but there are plans to go back and test this. But the most important thing is that each lander will contain laser retroreflectors, and they will expand the current network, and they will contain the next generation of retroreflectors that will give us that precision that is needed to make some fundamental advances. And the goal here is to put 4 identical landers down. Yes, there's going to be one on the far side, and they will have retroreflectors, just in case we have a non-optimal landing of a near side station, so we can put it on the near side and still get our science. I'm going to be active for 6 years with a goal of 10. And having that much wider distribution than the Apollo seismic data, we're going to be able to look at the interior and really study the interior structure and composition of the moon to understand that initial stage of terrestrial planet evolution. Now, I'm going to switch gears to the biology side, and physical sciences come back Friday morning because there's a lot for you in the future. Trust me on this. So just have to come back bright and early, well, early Friday. So I want to call out a number of publications that sort of do the reviews of the state of the art. And this is a book published in 1989, Lunar Base Agriculture. And it contains a lot of rich information about where we were in 1989, our current state of understanding, but also the possibilities of using the moon to support life, to actually grow crops, to have bioregenerative life support systems. The other one is Rob Furl and Annalisa Paul, their review paper in astrobiology in 2010 that went back and looked at the Apollo era data on plant biology. And one of the great things about this is a bibliography that's in a table in this paper, and I've highlighted the URL that you can go to get further information on each one of these papers, that most of which are in the what we term grey literature, i.e. they're very difficult to find, i.e. you may have to physically go to a library and look at a book. Foreign concept these days. Yes, I've had students come up to me, I can't find this. I can't find it anywhere. I said, did you go to the library? What do you mean? Or did you go to the library? Did you walk over there and ask them? No, I just went online, couldn't find it. Okay, those two things hanging from your hips, use them, over to the library. Old school, I am getting old, what can I say? But these are some of the what I deem 2 fundamental publications in order to get up to speed with what has been done in this area. But there's a lot more that we need to understand. For example, the basic tenet of plant biology is that we need to be able to grow things in lunar regolith. That has not been done. Rob, correct me if I'm wrong, but to date, I don't think only lunar regolith has been used. It's been scattered on a substrate. Is that correct? So when you see, oh, we've already tested the toxicity, no, you've spread a little bit of regolith on there because the lunar scientists hold on to their lunar samples, and you can't use that for plant biology. And I know Rob and Annalisa have fought this battle and continue to fight this battle. But it's one of those things that can make a fundamental breakthrough if we can use return samples. And that's something to consider because the lunar regolith is very different to any regolith or soil we have down here. It has no organic matter. It is formed by impact. Impact to cause physical grinding, but also vaporization and recondensation that causes chemical changes. Iron oxide becomes iron metal. And you can see in the bottom left the nanophase iron that coats a lot of the particles in the lunar regolith. So as your regolith is exposed more to the space environment, it builds up more nanophase iron. And the ratio of iron metal to iron oxide, iron 2+, actually starts to increase. We also know that there are glass welded fragments called agglutinates. You can see in the bottom right there, those glasses contain bubbles. So there are volatiles present in the lunar regolith. Otherwise, why would you have vesicles in these impact melt glasses? Those volatiles become very, very important because if we look at the composition of lunar soils, lunar regolith, on the table on the right, and then you look at essential nutrient elements that are needed for plant growth, table on the left, we can see that there are some connections. And you'll notice that nitrogen and carbon are implanted by the solar wind. They're not indigenous, although there have been some organic materials found in lunar samples that appear to be indigenous to the moon, but very, very rare. So if we then look at our maturity index, which is metallic iron, ratio of metallic iron to FeO, and again, this is quantified by ferromagnetic resonance, we can see a positive correlation with hydrogen, carbon, and nitrogen. So the more mature our regolith is, the more of these nutrient essential elements are being implanted in the regolith by the solar wind, but not at the amount needed. So another idea that came up in this paper that came out this year was the idea of pioneer plants. Something to plant that may not be useful, but it will condition the soil so that we can then plant useful crops. So something that I think that is going to be needed if we're going to learn to live off the land when we send humans back to the moon and start a sustainable, long-term, enduring human space exploration campaign to the moon and Mars. Not moon to Mars, not moon or Mars, but moon and Mars. We got the Chang'e 4 experiment, the first green leaf on our barren moon. And thanks to Annalisa's presentation earlier this year, I stole this shamelessly, but you need the credit, Annalisa, because you're the expert. I'm a geologist. Let's just put it that way. But again, there was germination, but not in lunar regolith. These were self-contained experiments to see if germination could occur on the moon, and it did. So encouraging, but again, much more work still needs to be done. There's toxicology testing. It was done after Apollo. The first couple of Apollo missions, the astronauts went into quarantine in case they brought moon bugs back with them. It was shown that there weren't any moon bugs. So later missions astronauts did not have to quarantine. But then, how toxic was the material? This is well, let's expose plants to lunar regolith and just sprinkle some on the top and then see what happens to those plants. And again, this is well reviewed in the Furl and Paul 2010 paper. Mice were injected with lunar regolith to see how they did. Well, if you were injected with regolith, you probably wouldn't react that well to it. So I think the results were somewhat predictable. However, if you fast forward to the 20-teens, it was then using inhalable regolith particles on rats. to understand what happened with them. And again, this is something that gave us an idea of toxicity to humans, that we could have no adverse effect levels that could be predicted for humans. So toxicity testing, again, looking at the fundamental regolith itself, it's very different from what humans are used to. This is something that we need to take into account as we start to craft systems for mitigating dust and also for keeping the humans and the dust apart. And again, we've got lots of space applications for geomicrobiology, and I've given you a list there that comes from the ESA roadmap for geobiology in space exploration from 2016. And these, you can see planetary protection is there, both forward and backward. This has an initial origin back in 1970, again, when it was deemed that the lunar regolith was devoid of life. But what about biomining? Workshop held at NASA Ames in 2007 had a lot of applications for using microbiology to get resources out of the moon. And the conclusion was more research was needed, or more research has been done, and suggests that there are some hurdles to overcome, but this is a path that should be pursued in order to liberate resources from the lunar or Martian regoliths. And again, recycling. We need carbon and nitrogen. And again, sort of the idea of this has been brought to the forefront in the film The Martian there. But again, actually using and what they call synthetic biology, a new term I've learned, that the engineering of systems, especially the biological portions of those, become very, very important, because we really need to get beyond near-Earth vicinity. We can't keep doing resupply. I don't care how cheap SpaceX says its launches are going to be. If you get out to Mars, you can't bring everything with you. You get out to the moon, you can't afford to bring everything with you. You set your program up to be cancelled. So we have opportunities. We have a new space policy that's enduring, and we have a unique time. We have a space policy that's transcended an administration. So we have opportunities then for this community to help get humans back to the moon in a sustainable, long-term, and enduring way. Well, here are those opportunities. And I've not listed all of them. But it's important to look at these and look at the synergies between the community that I come from, the lunar science community, and the communities that you come from. And again, welcome home. We can now talk to each other again. How about that? So, in summary, we're going to go to the moon, and this time to stay. It's going to require a community effort of many communities to do that. And much has been done, but much more work is still needed that needs to be coordinated. And what we have learned is that the moon holds possibilities, a lot of possibilities, for humanity surviving and thriving there and advancing all of our science about the solar system, about humans, about the moon, etc. And again, the moon represents important opportunities for the biological and physical sciences. And I think that's something that can be done both through robotic and human exploration. And again, I'll talk more about that on Friday. And again, future opportunities will allow ground truth lunar surface experiments. Thank you very much.
We've got some questions coming in. Again, 855-1413. I feel like I'm selling something. So can you talk about the consistency of mineralogy across the moon?
Consistency of mineralogy across the moon. Well, you've got two basic divisions. You've got the white areas when you look at it, the highlands, dominated by the mineral plagioclase feldspar. And then you have the basaltic terrains, or the mare, the darker areas when you look up at the moon. They're the two basic subdivisions. So if you look at this planet, you look at volcanic soils. They're very rich in terms of being able to grow crops. So you have a lot of fertility around volcanoes on this planet. But we do lack the organic matter. And we do lack some of the nutrients that are needed. So this will have to be engineered. But the basic mineralogy between those two different terrains, you can split it into the basaltic or the highlands or the plagioclase-rich areas.
So we also have a question. A plant growth on regolith will require a specific range of particle sciences. So when spice mining actually happens, will space mining be available to bag specific particle sizes for farming? Are you aware of anything?
Yeah, well, again, this is something that we already have in the sample collection. You can look at the different grain sizes. Basically, you get a reduction in grain size to a steady state the longer it's exposed to space weathering. And the sieving that's been done down at Johnson Space Center on regolith that was brought back by Apollo shows you a whole range. I refer you to the Lunar Source book, where Dave McKay's chapter in there gives you all the gory detail about the different grain sizes and the different size fractions depending upon the maturity of the regolith.
I'm sorry, we're kind of pressed on time here, but I'm going to give one question for some of the younger folks in the audience. Which research area do you see has the most pressing need for establishing this sustainable presence on the moon? So out of all that list, what would you give the young people advice to focus on maybe?
Well, I'd say food and life support. You need to be able to grow food to sustain humanity. And they need to be able to breathe and drink water.
Well, there you go. Well, thank you very much, Dr. Neal. That was wonderful. I really appreciate it. I think I'm going to do my